Okay, perfect. Yeah, so this is going to be based on the work that was done in collaboration with Sid Mishra Sharma and Cora Dworkin. And in the interest of time, I will only highlight some of the parts of this work. But yeah, please check it out if you're interested in more details. So this talk is going to be on data compression and inference in cosmology with self-supervised machine learning. So just the brief outline, I will first talk about the motivation for this work. I will then move on to self-supervised learning framework and the method that we used in this project. And then I will talk about two applications of self-supervised learning in cosmology, in particular data compression and marginalization over systematics and nuisance parameters. And then I will move on to conclusions. So for the motivation, current and upcoming surveys such as DESI, Euclid, Vera Rubin Observatory, and SKA will provide massive amounts of information to probe some of the new and existing questions in cosmology. And making full use of these data sets is going to be a challenging task. In part because analyzing the raw data is computationally expensive. So oftentimes the data is first reduced down to a set of some informative summary statistics, such as power spectrum, bispectrum, wavelet scattering coefficients, and so on. However, some of the potential considerations associated with using the summary statistics is that they might not encode all of the physically relevant information from the input data. And then also, even as a summary statistic, these data vectors could potentially be very high dimensional, especially when it comes to like multi-probe analysis. So, and there's been a number of works that looked at different ways of constructing compact or low dimensional summary statistics that are still optimal in the sense of the amount of information that they encode. So in this work, we took the approach of self-supervised learning with physically motivated augmentations as a way to construct these informative summary statistics. Okay, so just the overview of the self-supervised learning pipeline. In general, self-supervised learning combines unsupervised elements of unsupervised and supervised learning, and it breaks down this learning process typically into two steps. So in the first step, which is called the pre-training step, so in the first step, the pre-training step, the neural network that's called encoder learns how to compress the initial input data vector into a summary statistic by first being given two different views or augmentations that correspond to different transformations that we want the summary statistic to be insensitive to. So for instance, it could be cropping the image, it can be blurring the image or making it slightly off center, as in this example. And then the encoder is trained to produce low dimensional summaries of the input according to some loss function. And then once the encoder has been trained, you can use the summary statistics directly for the downstream tasks, such as classification, parameter estimation. And usually because the summary statistics are lower in their dimensionality, the second part involves a much simpler neural network, such as an MLP. So for our project, so there are different methods that have been proposed for the self-supervised training process. We decided to choose the variance, invariance, covariance regularization method, or VCREG, but other self-supervised learning methods seem to work just as fine. So this one uses a triple objective function, which tries to maximize the similarity of these summaries that correspond to the same image, while at the same time minimizing the redundancy between different features of the summary vectors, and also maintaining the variance between the summaries within a training batch so that the solution doesn't collapse to a trivial solution. And then finally, the downstream task for our work was the cosmological parameter inference. So we trained a simple neural network that we refer to as inference network to infer cosmological parameters of interest by minimizing this negative log likelihood function to predict the means and the covariance matrix for the parameters. Okay. So in this work, what we try to do is to slightly extend the self-supervised learning framework by including what we call physically motivated augmentations. And these are the augmentations or different views that correspond to the same underlying physics of interest, but perhaps different initial conditions or different evolution histories or different systematic parameters and so forth. Yeah, and so we looked at 3 different applications: data compression, marginalization over systematic parameters, and also parameter inference with simulation-based inference. But I will only look at the 2 of them in this presentation. Okay. So, right, the first application was data compression and parameter inference. And we first looked at a simple simulated model of matter density fields. We represented them by log normal fields. And the input data vector for us was the vector of different cosmological parameters. We only varied omega m and sigma 8, and then all the remaining cosmological parameters were fixed. And then in this case, our augmentations or different views were different realizations of the same input cosmology with different initial conditions that were also rotated and flipped at random. And then the encoder network compressed this 100 by 100 maps down to summaries of dimension 16. And the inference network basically predicted the means in the covariance matrix for the parameters. And then we took a look at how well the summaries encode the physically relevant information from the maps. We first assessed them by looking at their performance compared to the supervised baseline model, which was trained directly on the maps without any compression. And so what we found is that both the inference network trained on the summaries and the baseline supervised model gave fairly similar results in terms of the accuracy and precision. And then the next thing that we did is we decided to compare it to the Fisher constraints from the maps. So here I'm showing a plot of the Fisher constraints from the log normal maps, as well as of the posterior parameter distribution from normalizing flows trained on these summary statistics. And also for this particular fiducial cosmology, we found that the constraints show really great agreement, which also suggests that the summary statistics encoded a lot of physically relevant information for the parameter inference. Okay, so once we looked at this sort of like simpler simulated data, we moved on to the camel simulation set. And we used data from 2 hydrodynamical simulations, Elasticity and Simba. And we looked at total matter density fields, which represented the spatial distribution of baryonic and dark matter at redshift 0. So because it's a more complex data set, the size of the data set was fairly small compared to the previous one, but it contained 1,000 different cosmologies in each suit. Okay, and so for the different augmentations or views for our self-supervised learning setup, we used different spatial slices of the simulation boxes that were also rotated and flipped at random. And then once again, because of the complexity of the maps, we also found it quite helpful to modify the loss function to include 5 pairs of different augmentations, as opposed to just 1 pair in the previous setup. And then the encoder network compressed these 256 by 256 maps down to the summaries of dimension 128. And the inference network once again predicted the means in the covariance matrix for the cosmological parameters. So in this case, we also assess the summaries by looking at the performance of a baseline, what we call baseline supervised model, which is essentially a similar, a model with similar architecture that was trained directly on the maps. And we found that in this case, despite the reduction in the dimensionality of the data set, the inference network trained on these weak-rank summaries was still able to predict cosmological parameters with fairly similar accuracy. Okay, and then we moved on to using self-supervised learning for marginalizations over systematics and nuisance parameters. So this is kind of related to the previous talk. Baryonic effects tend to modify the matter power spectrum quite a bit on small scales. And in general, as was mentioned previously, these effects are very complex and poorly understood. However, it's going to be particularly important for future generation surveys. So one idea that we thought would be pretty interesting is to perhaps use these different implementations of baryonic effects in hydrodynamical simulations as different augmentations of the same cosmology with the same initial conditions. However, at the time as we were doing this work, this data set was unavailable. So instead we took a look at a very simple proof of principle example in which we looked at a 2 power spectrum model that it represents the power spectrum as a broken power law. So the first part is described by parameters A and B, which we refer to as cosmological parameters. And then the second part is described by this parameter D, which describes the power of the second part of the power spectrum, or the slope of the second part of the power spectrum, and it represents the effects of the baryonic physics. So in this model, the small scale still contain cosmological information or information about A and B through the parameter C. Yeah, and then there was no noise modeling, but we just accounted for some cosmic variance effects. And this is what different augmentations looked like for this data set. So different augmentations were the different variations in baryonic effects via the change in the parameter D. And then the encoder network once again compressed the initial data vector down to a smaller dimensional summary statistic. And the inference network, in this case, we wanted to see what it's going to give us when it predicts the means and the covariance matrix for A, B, and D. Yeah, so these were the results. As we can see, as we would expect, it can predict A and B pretty well, given the setup, but it doesn't have much information about the parameter D. However, we also wanted to check if this setup simply ignores the small scales or if it still contains some of the information from the small scales. And we did that by looking at two measures of dependence, distance correlation and mutual information, which essentially capture the information, capture both linear and nonlinear dependencies between different random variables. Okay, so these were the two data sets that we compared. In one of them, in the first one, D was just an irrelevant parameter, and then in the second one, D was a relevant parameter. So these are the results. As we can see, prior to the pivot scale, where the slope is, prior to the scale where the slope changes, both of these measures show quite similar trends. However, past the pivot scale, when we consider parameter D irrelevant, both mutual information and distance correlation decreases. And that's not the case when the parameter D is considered interesting or relevant. All right, so these are the conclusions. So in this work, we looked at self-supervised learning for cosmology. We considered a number of applications and explored its potential. However, before we actually deploy this method on real cosmological data sets, a number of follow-up studies are necessary, which include complexifying models, determining new ways of assessing how much we can trust the summary statistics, and also perhaps finding a more principled way to decide on the optimal size of the summary vectors.
Thank you.
Thank you.
So we have time maybe for two quick questions. One local here. Please, Douglas.
On? Oh, yeah. I mean, it sounds like you're marginalizing over baryonic effects.
In the second part, yeah.
I mean, I don't really understand that because presumably some of the simulations are correct and some of them are, let's say, less correct. So how do you marginalize?
So I guess the idea is that it's not often possible to figure out how, like, when it comes to baryonic effects, right? What we saw in camels is that different models give very different results for the total matter distribution. And it depends on, and this is like a part that we're not really completely sure about. So perhaps it is, if we want to, I guess, to extract some cosmological information from the simulations, and maybe we can be agnostic to different models and try to use them as augmentations and like kind of like not weigh them in different ways, but instead assume that they're all correct to a certain extent, but perhaps like not assume that one of them are more correct than others. I don't know if that answers the question.
Yeah, thanks.
Mm-hmm.
Yeah.
Okay. So Henry, do we have any question from Paris?
Yeah, we have a question from Paris, Paco.
Yes.
Hi.
Hi.
Just go ahead, state your name.
Yes, it's Louisa Lucy Smith here. Yes, so I wanted to know, do you have any insights on your, like what your summary statistics are actually encoding? And is it a lossless compression? And what is the size of your summaries? You know, some further insights on what those summaries actually are encoding.
Yeah. So the part over here was one of the things that we wanted to kind of like look at in terms of what exactly the summaries are encoding. So for instance, here, what we were plotting was the mutual information between the summary vectors and the values of the power spectrum in different bins. And so, for example, here, what we can see that the mutual information for the orange data set decreases, right? With when it comes to power spectrum in the smaller K bins, which kind of like indicates that the summary statistics don't really contain much information about the values of the power spectrum at this smaller higher K value, smaller scales. So in terms of whether this compression is lossless, we haven't really looked into that. And then for the size of the summary statistics, I tried to put it on the slides when it comes to like the encoder network architectures. But one of the things that we're still trying to figure out if there is a principled way of like choosing the size of the summary statistics.
Okay. So thank you very much, Aisan, for the main talk. And